In mathematics, big O notation describes the limiting behavior of a function when the argument tends towards a particular value or infinity, usually in terms of simpler functions. It is a member of a larger family of notations that is called Landau notation, Bachmann Landau notation, or asymptotic notation. In computer science, big O notation is used to classify algorithms by how they respond to changes in input size. In analytic number theory, it is used to estimate the error committed while replacing the asymptotic size, or asymptotic mean size, of an arithmetical function, by the value, or mean value, it takes at a large finite argument. A famous example is the problem of estimating the remainder term in the prime number theorem. Big O notation characterizes functions according to their growth rates. Different functions with the same growth rate may be represented using the same O notation. The letter O is used because the growth rate of a function is also referred to as order of the function. A description of a function in terms of big O notation usually only provides an upper bound on the growth rate of the function. Associated with big O notation are several related notations, using the symbols O, I copyright, I per mil, and I, to describe other kinds of bounds on asymptotic growth rates. Big O notation is also used in many other fields to provide similar estimates. Formal definition: let f and g be two functions defined on some subset of the real numbers. One writes, if and only if there is a positive constant m such that for all sufficiently large values of x, f, x, is at most m multiplied by the absolute value of g, x. That is, f, x, a equals an o, g, x if and only if there exists a positive real number m and a real number x o such that. In many contexts, the assumption that we are interested in the growth rate as the variable x goes to infinity is left unstated, and one writes more simply that f, x, a equals an o, g, x. The notation can also be used to describe the behavior of f near some real number a. We say, if and only if there exist positive numbers I and m such that. If g, x, is non-zero for values of x sufficiently close to a, both of these definitions can be unified using the limit superior. If and only if. Example, in typical usage, the formal definition of O notation is not used directly. Rather, the O notation for a function f is derived by the following simplification rules: if f, x, is a sum of several terms, the one with the largest growth rate is kept, and all others omitted. If f, x, is a product of several factors, any constants are omitted. For example, let, and suppose we wish to simplify this function, using O notation, to describe its growth rate as x approaches infinity. This function is the sum of three terms, 6x4, a 2x3, and 5. Of these three terms, the one with the highest growth rate is the one with the largest exponent as a function of x, namely 6x4. Now one may apply the second rule. 6x4 is a product of 6 and x4 in which the first factor does not depend on x. Omitting this factor results in the simplified form x4. Thus, we say that f, x, is a big O of. Mathematically, we can write f, x, a equals an O, x4. One may confirm this calculation using the formal definition, let f, x, a equals a6x4 a2x3 a plus a5 and g, x, a equals ax4. Applying the formal definition from above, the statement that f, x, a equals an O, x4, is equivalent to its expansion. For some suitable choice of xo and m and for all za axo. To prove this, let xo equals a1 and ma equals a13. Then, for all za axo. So, usage, big O notation has two main areas of application. In mathematics, it is commonly used to describe how closely a finite series approximates a given function, especially in the case of a truncated Taylor series or asymptotic expansion. In computer science, it is useful in the analysis of algorithms. In both applications, the function g, x, appearing within the O, is typically chosen to be as simple as possible, omitting constant factors and lower-order terms. There are two formally close, but noticeably different, usages of this notation: infinite asymptotics and infinitesimal asymptotics. This distinction is only in application and not in principle. However, the formal definition for the big O is the same for both cases, only with different limits for the function argument. Infinite asymptotics, big O notation is useful when analyzing algorithms for efficiency. For example, the time it takes to complete a problem of size n might be found to be t, n, equals 4n to a 2n plus 2. As n grows large, the n2 term will come to dominate, so that all other terms can be neglected. For instance, when n equals 500, the term 4n2 is 1000 times as large as the 2n term. Ignoring the latter would have negligible effect on the expression's value for most purposes. Further, the coefficients become irrelevant if we compare to any other order of expression, such as an expression containing a term n3 or n4. Even if t, n, equals 1,000,000 n2, if u, n, equals n3, the latter will always exceed the former once n grows larger than 1,000,000 equals 1000, 0003 equals u, 1,000,000. Additionally, the number of steps depends on the details of the machine model on which the algorithm runs, but different types of machines typically vary by only a constant factor in the number of steps needed to execute an algorithm. So the big O notation captures what remains. We write either or and say that the algorithm has order of n2 time complexity. Note that equal is not meant to express as equal to in its normal mathematical sense, but rather a more colloquial is, so the second expression is technically accurate while the first is a common abuse of notation. Infinitesimal asymptotics, big O, can also be used to describe the error term in an approximation to a mathematical function. The most significant terms are written explicitly, and then the least significant terms are summarized in a single big O term. For example, in the exponential series, expresses the fact that the error, the difference, is smaller in absolute value than some constant times when is close enough to 0. Properties: if the function f can be written as a finite sum of other functions, then the fastest growing one determines the order of f, n. For example, in particular, if a function may be bounded by a polynomial n, then as n tends to infinity, one may disregard lower-order terms of the polynomial. O, nc, and O, cn, are very different. If c is greater than 1, then the latter grows much faster. A function that grows faster than nc for any c is called superpolynomial. One that grows more slowly than any exponential function of the form is called subexponential. An algorithm can require time that is both superpolynomial and subexponential. Examples of this include the fastest known algorithms for integer factorization. O, log n, is exactly the same as O, log, nc. The logarithms differ only by a constant factor, and thus the big O notation ignores that. Similarly, logs with different constant bases are equivalent. Exponentials with different bases, on the other hand, are not of the same order. For example, and are not of the same order. Changing units may or may not affect the order of the resulting algorithm. Changing units is equivalent to multiplying the appropriate variable by a constant wherever it appears. For example, if an algorithm runs in the order of n2, replacing n by cn means the algorithm runs in the order of, and the big O notation ignores the constant. This can be written as: if, however, an algorithm runs in the order of, replacing n with cn gives. This is not equivalent to in general. Changing a variable may affect the order of the resulting algorithm. For example, if an algorithm's running time is O, n, when measured in terms of the number n of digits of an input number x, then its running time is O, log x, when measured as a function of the input number x itself, because now equals ai, log x. Product. Sum, this implies, which means that is a convex cone. If f and g are positive functions, multiplication by a constant, let k be a constant. Then, if k is non-zero, multiple variables, big O can also be used with multiple variables. To define big O formally for multiple variables, suppose and are two functions defined on some subset of. We say if and only if. For example, the statement asserts that there exist constants c and m such that where g, n, m is defined by. Note that this definition allows all of the coordinates of to increase to infinity. In particular, the statement that is quite different from that is. Matters of notation, equals sign, the statement f, x, is O, g, x as defined above is usually written as f, x, a equals O, g, x. Some consider this to be an abuse of notation, since the use of the equals sign could be misleading as it suggests a symmetry that this statement does not have. As de Bruage says, O, x, a equals O, x2, is true but O, x2, a equals O, x, is not. Newth describes such statements as one-way equalities, since if the sides could be reversed, we could deduce ridiculous things like now equals an2 from the identities now equals an O, n2, and n2 equals an O, n2. For these reasons, it would be more precise to use set notation and write f, x, a and O, g, x, thinking of O, g, x as the class of all functions h, x, such that h, x, a permil c g, x, for some constant c. However, the use of the equals sign is customary. Newth pointed out that mathematicians customarily use the equals sign as they use the word as in English. Aristotle is a man, but a man isn't necessarily Aristotle. Other arithmetic operators, big O notation can also be used in conjunction with other arithmetic operators in more complicated equations. For example, h, x, plus O, f, x denotes the collection of functions having the growth of h, x, plus a part whose growth is limited to that of f, x. Thus, expresses the same as. Example, suppose an algorithm is being developed to operate on a set of n elements. Its developers are interested in finding a function t, n, that will express how long the algorithm will take to run in terms of the number of elements in the input set. The algorithm works by first calling a subroutine to sort the elements in the set and then perform its own operations. The sort has a known time complexity of O, n2, and after the subroutine runs the algorithm must take an additional time before it terminates. Thus the overall time complexity of the algorithm can be expressed as. This can perhaps be most easily read by replacing O, n2, with some function that grows asymptotically no faster than n2. Again, this usage disregards some of the formal meaning of the equal and plus symbols, but it does allow one to use the big O notation as a kind of convenient placeholder. Declaration of variables, another feature of the notation, although less exceptional, is that function arguments may need to be inferred from the context when several variables are involved. The following two right-hand side big O notations have dramatically different meanings. The first case states that f, m, exhibits polynomial growth, while the second, assuming m greater than 1, states that g, n, exhibits exponential growth. To avoid confusion, some authors use the notation rather than the less explicit. Multiple usages, in more complicated usage, O can appear in different places in an equation, even several times on each side. For example, the following are true for. The meaning of such statements is as follows, for any functions which satisfy each O. On the left side, there are some functions satisfying each O. On the right side, such that substituting all these functions into the equation makes the two sides equal. For example, the third equation above means, for any function, there is some function such that. In terms of the set notation above, the meaning is that the class of functions represented by the left side is a subset of the class of functions represented by the right side. In this use the equal is a formal symbol that unlike the usual use of equal is not a symmetric relation. Thus for example does not imply the false statement. Orders of common functions. Here is a list of classes of functions that are commonly encountered when analyzing the running time of an algorithm. In each case, c is a constant and n increases without bound. the slower-growing functions are generally listed first. The statement is sometimes weakened to derive simpler formulas for asymptotic complexity. For any and is a subset of for any, so may be considered as a polynomial with some bigger order. Related asymptotic notations. Big O is the most commonly used asymptotic notation for comparing functions, although in many cases big O may be replaced with big theta I for asymptotically tighter bounds. Here, we define some related notations in terms of big O, progressing up to the family of Bachmann Landau notations to which big O notation belongs. Little o notation. The relation is read as is little o of. Intuitively, it means that grows much faster than, or similarly, the growth of is nothing compared to that of. It assumes that f and g are both functions of one variable. Formally, f, n, a equals ao, g, n as naa means that for every positive constant there exists a constant n such that. Note the difference between the earlier formal definition for the big O notation, and the present definition of little o. While the former has to be true for at least one constant m, the latter must hold for every positive constant, however small. In this way little o notation makes a stronger statement than the corresponding big O notation. Every function that is little o of g is also big O of g, but not every function that is big O g is also little o of g. If g, x, is non-zero, or at least becomes non-zero beyond a certain point, the relation f, x, a equals ao, g, x is equivalent to. For example, little o notation is common in mathematics but rarer in computer science. In computer science the variable is most often a natural number. In mathematics, the variable and function values are often real numbers. The following properties can be useful. As with big O notation, the statement is usually written as, which is a slight abuse of notation. Big omega notation. There are two very widespread and incompatible definitions of the statement. Where is some real number, or, where and are real functions defined in a neighborhood of, and where is positive in this neighborhood. The first one is used in analytic number theory, and the other one in computational complexity theory. When the two subjects meet, this situation is bound to generate confusion. The Hardy-Littlewood definition. In 1914 G. H. Hardy and J. E. Littlewood introduced the new symbol, which is defined as follows. Thus is the negation of. In 1918 the same authors introduced the two new symbols and, thus defined. Hence is the negation of, and the negation of. Contrary to a later assertion of D. E. Muth, Edmund Landau did use these three symbols, with the same meanings, in 1924. These Hardy-Littlewood symbols are prototypes, which after Landau were never used again exactly thus. Became, and became. These three symbols, as well as, are now currently used in analytic number theory. Simple examples, we have. And more precisely. We have. And more precisely. However. The Muth definition. In 1976 D. E. Muth published a paper to justify his use of the symbol to describe a stronger property. Muth wrote, for all the applications I have seen so far in computer science, a stronger requirement, a euro is much more appropriate. He defined. With the comment, although I have changed Hardy and Littlewood's definition of, I feel justified in doing so because their definition is by no means in wide use, and because there are other ways to say what they want to say in the comparatively rare cases when their definition applies. However, the Hardy-Littlewood definition had been well used for at least 25 years. Family of Bachmann Landau notations. Aside from the big O notation, the big theta I and big omega I copyright notations are the two most often used in computer science. The small omega I permil notation is occasionally used in computer science. Aside from the big O notation, the small o, big omega I copyright and notations are the three most often used in number theory. The small omega I permil notation is never used in number theory. Using computer science. Informally, especially in computer science, the big O notation often is permitted to be somewhat abused to describe an asymptotic tight bound where using big theta I notation might be more factually appropriate in a given context. For example, When considering a function, all of the following are generally acceptable, but tightnesses of bound are usually strongly preferred over laxness of bound. T, n, a equals n o, n 100, which is identical to T, n, a n o, n 100, T, n, a equals n o, n 3, which is identical to T, n, a n o, n 3, T, n, a equals ai, n 3, which is identical to T, n, aai, n 3. The equivalent English statements are respectively, T, n, grows asymptotically no faster than n 100, T, n, grows asymptotically no faster than n 3, T, n, grows asymptotically as fast as n 3. So while all three statements are true, progressively more information is contained in each. In some fields, however, the big O notation would be used more commonly than the big theta notation because functions that grow more slowly are more desirable. For example, if represents the running time of a newly developed algorithm for input size, the inventors and users of the algorithm might be more inclined to put an upper asymptotic bound on how long it will take to run without making an explicit statement about the lower asymptotic bound. Extensions to the Bachmann Landau notations. Another notation sometimes used in computer science is A, F, N, A equals AA, G, N is shorthand for F, N, A equals N O, G, N, A log G, N for some K. Essentially, it is big O notation, ignoring logarithmic factors because the growth rate effects of some other super-logarithmic function indicate a growth rate explosion for large-sized input parameters that is more important to predicting bad runtime performance than the finer point effects contributed by the logarithmic growth factor, S. This notation is often used to obviate the nitpicking within growth rates that are stated as too tightly bounded for the matters at hand for any constant k and any I micro AA0. Also the L notation, defined as, is convenient for functions that are between polynomial and exponential. Generalizations and related usages. The generalization to functions taking values in any norm vector space is straightforward, where f and g need not take their values in the same space. A generalization to functions g taking values in any topological group is also possible. The limiting process AXO can also be generalized by introducing an arbitrary filter base, that is to directed nets f and g. The O notation can be used to define derivatives and differentiability in quite general spaces, and also equivalence of functions, which is an equivalence relation and a more restrictive notion than the relationship f is I, g, from above. For example, 2x is I, x, but 2 x is not O, x. History. The symbol O was first introduced by number theorist Paul Bachmann in 1894, in the second volume of his book Analytische Theory, the first volume of which was published in 1892. The number theorist Edmund Landau adopted it, and was thus inspired to introduce in 1909 the notation O. Hence both are now called Landau symbols. These notations were used in applied mathematics during the 1950s for asymptotic analysis. The big O was popularized in computer science by Donald Knuth, who reintroduced the related omega and theta notations. Knuth also noted that the omega notation had been introduced by Hardy and Littlewood under a different meaning a per mil O, and proposed the above definition. Hardy and Littlewood's original definition is still used in number theory. In fact, Landau introduced in 1924, in the paper just mentioned, the symbols and precursors for the modern symbols and. Thus the omega symbols are sometimes also referred to as Landau symbols. Also, Landau never used the big theta and small omega symbols. Hardy's symbols were A and A. Hardy however never defined or used the notation, nor, as it has been sometimes reported. It should also be noted that Hardy introduces the symbols and in his 1910 tract Orders of Infinity, and makes use of it only in 3 papers. In the remaining papers and books he constantly uses the Landau symbols O and O. Hardy's notation is not used anymore. On the other hand, in the 1930s, the Russian number theorist Ivan Matveevich Vinogradov introduced his notation, which has been increasingly used in number theory instead of the notation. we have. And frequently both notations are used in the same paper. The big O originally stands for order of, and is thus a Roman letter. Neither Bachmann nor Landau ever call it omicron. The symbol was much later on viewed by Knuth as a capital Omicron, probably in reference to his definition of the symbol omega. The digit 0 should not be used. See also, asymptotic expansion, approximation of functions generalizing Taylor's formula, asymptotically optimal, a phrase frequently used to describe an algorithm that has an upper bound asymptotically within a constant of a lower bound for the problem, big O in probability notation, op. Computational complexity theory, a subfield strongly related to this article, limit superior and limit inferior, an explanation of some of the limit notation used in this article, Nachbin's theorem, a precise method of bounding complex analytic functions so that the domain of convergence of integral transforms can be stated, references and notes. Further reading, Paul Bachmann. Die analytische Zochentheorie. Zochentheorie PT2 Leipzig, B.G. Tübner, 1894. Edmund Landau. Handbuch der Leuven der Verteilung der Primzahlen 2 vols. Leipzig, B.G. Tübner, 1909. G.H. Hardy. Orders of Infinity, The Infinite Currency RCALCA 1/4 L of Paul Du Bois Raymond, 1910. Donald Knuth. The Art of Computer Programming, Volume 1, Fundamental Algorithms, 3rd edition. Edison Wesley, 1997. ISBN 0-201-89683-4. Section 1.2.11, Asymptotic Representations, PPA 107 123. Thomas H. Corman, Charles E. Lesserson, Ronald L. Revest, and Clifford Stein. Introduction to Algorithms, 2nd edition. MIT Press and McGraw Hill, 2001. ISBN 0-262-03293-7. Section 3.1 Asymptotic Notation, PPA 41 50. Michael Sipser. Introduction to the Theory of Computation. PWS Publishing. ISBN A0-534-94728-X pages 226 of Section 7.1 Measuring Complexity. Jeremy Avigad, Kevin Donnelly. Formalizing O notation in Isabel H. Hol, Paul E. Black, Big O notation, in Dictionary of Algorithms and Data Structures, online, Paul E. Black, ed., U.S. National Institute of Standards and Technology March 11, 2005. Retrieved December 16, 2006. Paul E. Black, Little O notation, in Dictionary of Algorithms and Data Structures, online, Paul E. Black, ed., U.S. National Institute of Standards and Technology December 17, 2004. Retrieved December 16, 2006. Paul E. Black, I copyright, in Dictionary of Algorithms and Data Structures, online, Paul E. Black, ed., U.S. National Institute of Standards and Technology December 17, 2004. Retrieved December 16, 2006. Paul E. Black, IPamil, in Dictionary of Algorithms and Data Structures, online, Paul E. Black, ed., U.S. National Institute of Standards and Technology November 29, 2004. Retrieved December 16, 2006. Paul E. Black, I, in Dictionary of Algorithms and Data Structures, online, Paul E. Black, ed., U.S. National Institute of Standards and Technology December 17, 2004. Retrieved December 16, 2006. External links. Online Encyclopedia of Integer Sequences, Introduction to Asymptotic Notations, Landau Symbols, Big O Notation. What is it good for?